Hey all, so in this our last section we're going to look at partial fractions, and they are a bit challenging. They won't show back up again until Calc 2, but you will need them for an integration technique that you will learn then. Partial fractions, so what are they? They are kind of the reverse of adding. They're decomposing a fraction into its parts. So let me take this one down. I'm going to write it over here and just make it a little bit bigger. 2x minus 1 plus 3x plus 2. So in a previous class, hopefully you learned to add things like this. We would multiply this one by x minus 1, x minus 1. We would multiply this one by x plus 2, x plus 2. And so we are, clean that up there. I still drew through it. Anyhow, we're finding a common denominator so that we're able to add the numerators here in a second. So the same way if it was 1/2 and 1/3, I'd multiply this by 3 over 3 and this by 2 over 2. I'm just finding a common denominator. So this would be 2 times x plus 2. I'm just going to write that out as it is. This would be 3 times x plus 1 or minus 1. And all of that is over x plus 2, x minus 1. And then we would combine up the numerator and get 2x plus 4 plus 3x minus 3 over that common denominator there. And then 2x and 3x would be 5x minus 1 over x plus 2 and then x minus 1. So, oops, that should be a plus right there, sorry. So what we're trying to do in this section is we're going to start with this piece, and we're going to try to decompose that into its partial fractions. We're going to try to get back here. So that's kind of the goal. It's the reverse of adding or subtracting fractions. We're now decomposing to those partials. We're going to have two methods for doing that, and I'm going to show them here. And notice, so this is where I should get back to each time. For each of these linear terms that I have down in here in the denominators, I end up with some constant up here in the numerator. So the first thing I'm going to do is kind of set this up as equals. I don't know what that constant is, but it's going to be over x minus 1 because I can see I have that in my denominator. Likewise, I don't know what this one's numerator is going to be, so I'm just going to call it b for now. But I know that the denominator is x plus 2. So now I have this equals these two fractions, and we're going to clear the fractions by multiplying both sides by the common denominator. And so the same thing over here. Oops. On the left-hand side, this all cancels, and I'm just left with 5x plus 1. On the right-hand side, here, if you picture this x minus 1, x plus 2 sitting in each of these numerators like I distributed it through, the x minus 1s would cancel on the first round, and I would have a times x plus 2. And then here, if this was sitting up in that numerator, the x plus 2s would cancel, and I would have b times x minus 1. So this first method is a good one if we have, we're trying to find two things. We're trying to find a and b, and I have two zeros in my denominator. So the zeros from the denominator can be used in this altered equation that we have down here where we cleared the fractions to solve for a and b. And if you have as many zeros as you have variables, you're golden. Just plug in the zeros. I'll show you that in a second. And the method one works really well. So for my zeros, I would have x equals 1 would be my first one. And we'll plug that in to this, so that would be 5 times 1 plus 1 equals a, and then 1 plus 2, and then 1 minus 1 would make 0. That's why we like that, is because it makes this term 0 and cancels out that b. So I have 5 plus 1 is 6 equals 1 plus 2 would be 3a, and then it looks like from there a would be 2. the same thing with x equals -2 because that's my other 0. So 5 times -2 plus 1. If I put -2 in for that x, it knocks out that term. So then I just have b -2 minus 1. So that would be -10 plus 1 would be -9 equals -3b. And then from there, b equals 3. So that means my solution to this thing, with my a's and my b's, I should have 2 over x minus 1, and then 3 over x plus 2, which if we look back at the example that we did here, oops, there's the 2 and the 3 that we got when I decompose this that I should get back is those two constants. So that's the goal. Method 2, I don't love this one when I have zeros. I'd rather just plug in the zeros. I think that's easier. But when you don't have zeros or you don't have enough zeros, method 2 can be helpful. You can also kind of do a combination of the methods as well. For this, the first part is the same, so I'll just kind of slide through that real quick. And you would still multiply both sides by the LCD, so I'll just go like this. And we'd get to that exact same equation I had in the last example. So 5x plus 1 equals a, and that'd be times the x plus 2, and b would be times the x minus 1. But this time, instead of using the zeros, because sometimes you don't have any zeros, and then that complicates things, I'm going to distribute through the a and the b. So that would be ax plus 2a plus bx, and then minus b. I'm going to group up my x's together and my constants together. So this would be ax plus bx, just kind of writing the like terms next to each other, and then plus 2a minus b. And lastly, I'm going to factor that x out just to make this a little easier to see. And I'm going to have a plus b times x. So if I distributed the x through, it would be just this again. What that helps me do is see that a plus b would be the coefficient on that x term. And then plus, throw some parentheses around these just to kind of show that those are a group. So then we can match up each side of the equation. Over here we have 5x. Over here we have a plus bx. So that means that a plus b must equal 5. Here we have the plus 1, and then these are our constant terms. They didn't involve x at all. So that means 2a minus b is going to be equal to 1. And then I can set those equal. So a plus b equals the 5, and 2a minus b equals that 1. And this is why this is in this section, is because now we have a system of linear equations. And these ones actually turned out great. I can just add those together. The b's will eliminate. And I have 3a equals 6 and a equals 2. Plugging that back in here and back solving, 2 plus b equals 5. And b equals the same 3 that I got back there. There's the same 2 and 3. So that is the second method. Again, if you have zeros, I would use all the zeros. There's one example that I'll show here where we only have 1 0. I would still use it because it simplifies things a bit, and then switch over to method 2 if you don't have zeros left. And that's pretty much what this says. So method 1 is good if you have lots of zeros. Method 2 is better when you don't have many zeros. In terms of how to set these up, this box looks really complicated, and I'll try to simplify it down here a bit for you. But when we have non-repeating linear terms like this, and non-repeating means they're not squared, there's just a single one of them, what we do is we set up a over the first term plus b over the second term, and it wouldn't matter if I wrote those backwards. You could label that one a and that one b. You would get the same answers once you plugged in your constants. If there was a 3 over x plus 1, it wouldn't matter if you had labeled it a or b. You would still be over the x plus 1 term. And that's it for non-repeating linear terms. For repeated linear terms, and we won't do one like this, but let me show it real quick over here. Let's say we had 1 over x plus or minus 3 squared. That would set up to a x minus 3 plus b x minus 3 squared. And it'll make this one a little bit easier to see. But so it's a linear term, it's x minus 3. It happens to be squared, but that's the repeating piece. The ones that we will see are like this one, where this denominator still needs to be factored, so let me do that. So we'd have x squared plus 25 up top, and downstairs there's a common factor of x squared, so I take that out front, it's x plus 4. X squared can be written as a repeated linear term because it's just x twice, so it's kind of the too easy it's hard one. So this would be a over x plus b over x squared. So that's taking care of if there was an x or an x squared term, we would still get this x squared here. And then there's our last linear term, which is c over x plus 4. So if I have x squared and x plus 4, I could get this denominator. I don't necessarily, a could end up being 0. I could just have those two, because x squared plus or times x minus plus 4 would still give me the same denominator. And you don't know until you solve. Sometimes some of these will end up being 0 in some cases. For this last one, we have an irreducible quadratic. I'll scoot it out here. So that's x squared plus 3, which is to say I couldn't factor this any further. If this was like x squared minus 4, I'd want to write it as x plus 2, x minus 2. I'd want to break it down to its linear terms. But this doesn't factor, so we're stuck with that. And then x minus 7. So when it's a linear term, it gets a constant. When it's a quadratic term, it gets a linear term. So that would be ax plus b, which is what this one right up here is showing for the quadratics. And then this would just get a c. So squared gets x to the first gets a constant. So there's a little brief on how to set these up, and the ones that we're going to see are going to behave just like these. This next example, so find the partial fraction for this. The first thing we want to do is factor the denominator and see what we got. And this is going to be x minus 3. Write this in the same order in my notes, so it'll be easier. So I'm going to write the 1 first, just so it'll be easier to track with the notes, and x minus 3. So it's very similar to the example that I just did. We have 2 zeros. When I set up the right-hand side, it's going to be a over x plus 1, and then b over x minus 3. So very similar to what we just did. We'll do LCD over here. And this side, it always cancels out, which is why we're using it. On this side, we'd have a, and then x minus 3 plus b. X minus 3's cancel, so that would leave x plus 1. And I have 2 zeros and 2 unknowns, so that's great. We'll just use our zeros. So we'll start with x equals negative 1. So 2 times negative 1 minus 1. And that'll be a negative 1 minus 3 right there. So that will be negative 3 equals negative 4a. So a would be dividing that over 3/4. And we'll do the same thing with 3, since that's our other 0. So 2 times 3 minus 1 would equal, this piece would drop out because 3 minus 3 would be 0. So b, and then 3 plus 1. So 6 minus 1 would be 5, and 4b, and we divide that over, and we get b equals 5/4. So in terms of the answer, I think on the computer you get to just type those into boxes. For writing this out on paper, it would look like 3 over 4x plus 1. So instead of having the 3/4 in the fraction, because that would be a complex fraction which isn't simplified, we put it in the denominator, plus 5/4 x minus 3. Get that scrolled up. Okay, so this next one is a little bit harder in terms of the factoring, so let me remind you how to do that. I think I'll just scoot up here with it, kind of do the scratch work. So remember, for these, this doesn't lead with a 1, there's no GCF, and I think I'm just going to erase that so I have a little more room. We would go a times c, and we would get 24 in that case, and then we need two numbers that multiply to be a times c, 24, and add to be -10. So that's going to be -4 and -6, because they multiply to be positive 24 and add to be -10. And then remember, we do x squared, or 8x squared, and we'll go minus 4x minus 6x plus 3. And then we're doing our factor by grouping from here, so that's going to be a 4x out front, leaves behind 2x minus 1. And then from those two, we would take out a -3 and again a 2x minus 1. So my factored version is going to be 2x minus 1 and 4x minus 3. From there, it sets up just like the last one. So we'd have a over 2x minus 1 plus b over 4x minus 3. Get that scooted up. And then from here, I'll multiply through by the LCD. Just write LCD this time, which would be 2x minus 1, 4x minus 3. There it all cancels, and we're left with 42. Here I'd have the 4x minus 3 would survive because the x squared minus, or x minus 1, 2x minus 1s would cancel. So that would be, excuse me, a times 4x minus 3 plus b, and then that would be times the 2x minus 1. So this time the x's are a little bit harder, so we're going to let x equal 1/2. Oops, there should be an x right there from there. So 42 times 1/2. And then the half would knock out this one, because that's 1/2 is this one 0. So I brought the 1 over and divided by 2 to be x equals 1/2. So this is gone. So I just have to contend with this piece. So a and then 4 times 1/2 minus 3. So half of 42 would leave 21 over there. Half of 4 would be 2, minus 3 would be -1. So that would just be -a. And then that means a would equal -21. And then we'll let x equal, it would be 3/4. So 42 times 3/4. And that's going to equal b times 2 and then 3/4 minus 1. And so with this, you can do it in fractions. I went ahead and I did this one in decimals just to show that you can. So if you go 42 times 3 divided by 4 on your calculator, if that came out to some non-repeating type decimal, that wouldn't be great, but it comes out to 31.5, so that will work out just fine. Likewise over here, 2 times 3/4 minus 1 would be 6/4, or 3/2 minus 1 would be 1/2. So again, I just thought of it as a decimal, so 0.05b. and then we can divide that over, and you should get b equals 63 when you do that. So then the answer would be negative 21 over 2x minus 1 plus 63 over 4x minus 3. So these last two examples, I cannot write small enough on the whiteboard for it to be legible, and so I'm going to take a picture of the notes here, and I'm just going to talk through what I wrote on paper, because again, I can't write small enough to make that actually fit on a Zoom whiteboard. So for this one, we have, let me make that bigger for just a second. Oh, it's not going to let me do that. There we go. So this initial part is x cubed plus 5x squared. And so what I'm doing is I am factoring out an x squared and getting x squared x plus 5. So let me see if I make that smaller again and make it not blue. Oops. Okay, it may just stay blue. Okay, I'm running with it. Yeah, it's not letting it. Oh, there we go. Okay, better. So there's our x squared x plus 5. And then on this side, that's a little better. So that x squared was like I showed earlier. It's actually a repeated linear term. It's an x and then an x squared and then the x plus 5. I used my LCD on both sides, so that canceled everything over here, and I just have this left. Here, if you picture that x squared, x plus 5 in each of these numerators, for the first one, one of the x's would cancel, and I would just have x minus 5. Here, they would both cancel, so I have x plus 5. And on the last ones, the plus 5's cancel, so I have x squared. On this, I have 2 of the 3 zeros I need. I need to find an a, b, and c, and I have x equals 0 and x equals negative 5 that I can use. So that's what I'm going to do first. So if I let x equal 0 in this equation, this drops out and I just have 13. Anything with an x term in it is going to drop out because 0 times who cares, this stuff is 0, and same thing over here. So this is the only term that would survive, and then 0 plus 5 is 5, and then 13/5 for b. Did it again. Stop it. Okay. For this next part, I let x equal negative 5 because that's my other 0. So similarly, putting negative 5 in there, and that became 25 and 13 for 38. Anything that had a x plus 5 in it would drop out, so that just left me the cx squared term. And squaring that, I get 25, dividing over 38 over 25. And then I have these two kind of crummy fractions and this equation, so what I did next was, I know b and c, I don't know a, so I made up a third number, and I just picked the easiest one I could think of, which was 1. And I'm plugging that in for all the x's. I know b is 13/5, so I can put that right there. I know c, it's 38/25, I can put that right there. And then with the x's being 1, that lets me solve for a. And that's what the rest of this is, and it's just kind of an exercise in fractions. So plugging the 1 in for all the x's, on this side I got 1 squared plus 13, so that's a 14. 1 plus 5 would be 6 times a, made the 6a. 1 plus 5 there would be 6, and then 6 times 13 is how I got that 78. And 1 squared just left the 38/25. So for what I have in blue, I am looking at that going, I have fractions involving factors of 5, so my LCD is going to be 25, and so I wanted to get all my fractions up to denominators of 25 so I can combine my terms. So for this one I did 5 over 5, which got me right here, and for the 14 I did 25 over 25, which got me that fraction. Next I did 390 plus 38, and that got me the 428, and that's still there. I'm going to keep doing that this whole time. Oops, nope. And then subtracted this over, that's how I got the negative 78. And then since I had 6a left, I multiplied both sides by 1/6 so I wouldn't have a fraction over a whole number trying to divide. And then the 6 went into the 78 13 times. And so there are all of my A's, B's, and C's. Much harder than what I would pick for a test, but sometimes that is what the numbers do. This last one is similar, except this time I have a non-repeating quadratic term right here and one linear term. So for this one, since it has an x squared and I can't break it down to something times something, when it was x squared I could break it down to x times x, but this I can't. So that's where we get the ax plus b in this numerator and the c for the constant term. Same thing, I'm clearing the fractions with the LCD, and that got me to this line. So there the x squared plus 3's are canceling, and there the x minus 7's are canceling. I only have 1 0, but I'm going to use it because I can at least get rid of a little bit of this and simplify down here if I know one of the values. So since x equals 7 is a 0, I plug that in, and I get some big numbers, so I'm plugging it in right here for all these x's. 7 minus 7 would drop this part out, but it lets me solve for c. So there's a 7 in for the x, and I got 490, 7 times 34 for that, minus 44, and then collecting all these terms on this side, I got 208. Over here, plugging in for c, 7 squared would be 49 plus 3, that made 52c. Dividing that over, c equals 4. So, let's see how many times I can manage to do that before I get to the end of this. What I'm going to do here is take this equation, and now I know what c is. C is 4, and so I'm going to plug in 4 right there. I'm also going to FOIL this out and switch over to method 2 for the rest of the problem, which will be not too bad once we get through this part, the messy part. So foiling ax times x got the ax squared, ax times the negative 7 right there, b times x right there, b times negative 7 right there. And then putting the 4 here on this next line, everything else is the same. I just distributed the 4x squared and plus 12. So if you notice, these do not involve a, b, or c anymore. These are just things that are known, so I can move them over to this side and combine them with their like terms. So that's why I did minus 4x on both sides to get rid of this, and minus 12 on both sides to get rid of that. Doing that over here got me the 6x squared, brought the 34 down, and then negative 44 minus 12 for the negative 56. Like the example I did on the first method 2 one that I did earlier when I was introducing it, ax squared, that's my only x squared term. The 7ax and the bx, those go together, so I'm factoring the x out, and I can see my coefficient there. And then that minus 7b is right there on the end. So now I can match up my coefficients for each of my terms. So 6x squared has to match the ax squared, which means 6 equals a, which I have right there. Negative 34, it's in front of the x, so that has to match with this one. So I would have minus 7a plus b would equal minus 34. And then here, minus 56 has to equal the constant term, which is minus 7b. So that's what we have right there. I already had a equals 6. Cool, we got that. Dividing that 7 over, that gave me b equals 8, so I didn't have to mess around with solving that one. And then plugging back in, we get the 6 and the 8 and the 4 in for the A, B, and C. So again, that one is also pretty tough, harder than I would pick as an exam question, but in terms of the homework, there's probably a couple of that level.